Assalamu alaikum, everybody. My name is Suleiman Adebayo, and today I'll be giving my seminar presentation on this very simple but powerful topic, which is the noisy student training. This will be the outline of the presentation. From the introduction, we talked about the motivation, then we see what is this method we are talking about. Then we can see this noise and this type of noise. Is it kind of the sound noise or the car noise? What type of noise we are interested in? Then we see a sample use case, which is a paper that make use of the work or of the method. Then we can round it up from there. When we say noisy students, what do we mean by the noisy students? Do we mean something like this? Obviously, no. So we are not talking about something like this. When we say noisy student in this context, so we are referring to machine learning models, actually. So this is a brief overview of the brief introduction of the noisy students. When we say noisy, most likely there is a student. When we say student, most likely there is a teacher somewhere. So we have the concept of. We can also say the concept is teacher-student training. So, but we are actually interested in the noisy part, which is how they added some noise to the training. But in this regard, so we have a normal supervised learning where we have annotated images that is well labeled. Then we use it to train a model. Then we get our result. So, but here we actually have a teacher model that is trained on a standard data. Then we use that teacher model to train a new student model. Then in this case, the student label can also train more student model as much as we want. This will be more clearer in the concept when we say the method overview. What is the motivation of this concept? The motivation is very simple and straightforward. We have labeled data sets, which is costly and not readily available, especially in the volume that unlabeled data set is available. It's easier when we go to the internet, we find millions, if not billions, of images that are available, that are free, but they are not well labeled, so they are not well annotated when we want to use it for machine learning training. The goal is to have something that's okay. This unlabeled data set that is readily available, is that way we can use it in our model too. When we do that, we will be getting improved accuracy. So we will be getting improved accuracy and we'll be getting improved robustness. So improved robustness in the sense that we have more data set, then our model will be able to behave well in a new situation, in the situation that it has not seen in the past. This is the method, very straightforward method. We have a teacher model, which is just any standard supervised learning model, so which is trained on a labeled data set, which is maybe not as much as available as the unlabeled one. So this new teacher model, we can say this new trained model now will now be the one to perform the annotation task. Instead of having human being to sit down and be annotating 1 billion images, that's a lot of work and it's also prone to error. So now the model will do that, which is the teacher model will do that. So after doing that, now we will now have a new model which will be trained on the originally labeled data and the new available unlabeled data. So it will be trained on this set of data sets. That means it will be trained on more data sets, and we can also iterate it in many times to get a different result based on the use case. So this is just the general idea of this noisy student. But when we say noise, which type of noise do we mean? We can have two categories of noise. So it can be the input noise, which is the data augmentation. We can do some flipping, some rotation, and a lot of things. But this example, we can say, okay, we just want to do rand augment. Or we can do model and noise. by using some dropout or stochastic depth. So in this, by doing this now, we are training the students in a more difficult environment, in a more difficult situation compared to when we are just using the good, well-structured data set, and when we are not adding any noise. So when we do this, we train the student, and as I've said, in a very difficult situation, but that implies that it will be able to identify, perform well in difficult situations as well, since that's the environment it is being trained. This is a sample paper that I make use of this simple but powerful approach. So it's research from the Google research, the Brain team, and the CMU researchers. So this paper was published in 2020, and till today, that before I make these recordings, they have 3,261 citations from Google Scholar. This is their result. I just picked one result from the paper. They test it on the ImageNet. Here, the black label is the performance, what the noisy student model say about the image, and the red label is what another model that is not trained with this approach say. So we can see that this noisy student model is even able to perform well, almost better than human being, because at times, if let's say assume we've not seen this label, it's easier for human being to even misclassify these images. Let's say this swing, for example. Now it's very difficult to see what is there, and this plate rack, it's you don't know, maybe it's a medicine check, or maybe it's a refrigerator, a lot of things. So this is it's able to perform well in a very difficult situation. That's the robustness we get from the noise, but we get the advantage of using more images with this unlabeled data, which is actually labeled for us by the teacher, which is also part of this very big concept. To round it up, so this is mostly from the paper, the sample paper. So the noisy student training is simple but also powerful, as I've said, because it gives us the opportunity of using very large data set in case we have a use case or an application that need to be used, a very large data set. So by adding noise too, so we allow the student to be larger and be better than the teacher. So because it's actually trained on bigger images, or we can see larger images, and it's also actually trained on a more difficult environment than the teacher label, than the teacher model. So in this paper, when they try it on the ImageNet classification, they are able to actually have a new top 1 accuracy, and it's not only that, with that they are also able to achieve very good robustness, in which the model is able to perform well in very difficult situations. And thank you so much for your time, and I don't think we have any questions here, since this is a recording and this is the reference paper in case anybody is interested. Thank you. Assalamu alaikum.